Right now, across the globe, digital platforms are processing billions of user inputs. Swipes, clicks, purchases, and video streams are all resolving simultaneously, without crashing the system. But software wasn't always capable of this volume. Early programs were written sequentially, as a single top-to-bottom list of instructions. If an error occurred on line 50, it cascaded down, breaking everything below it. The code was fragile, and adding new features meant untangling thousands of lines of dependent linear commands. To solve this, developers shifted to object-oriented programming, or OOP. Instead of writing sequential lists, they began modeling software on physical, real-world entities. They started designing code as distinct, self-contained items, with their own specific traits and actions. By isolating code into these self-contained units, developers ensure that a change or a bug in one specific part of the system doesn't automatically cascade through the entire program. This modularity provides the structural integrity required to build and maintain large-scale applications. The foundation of this system starts with a class. A class is purely conceptual. It's a template or a blueprint that outlines the properties and behaviors something should have. Because it is just an idea, it consumes zero active memory in the computer. An object, on the other hand, is the real physical manifestation of that blueprint. When a class is actually created in the software, it becomes an object, and at that moment, it takes up physical space in the computer's memory. To bridge the gap between that theoretical blueprint and the physical item, programmers use what is called a constructor. This acts like a factory. It takes the conceptual pattern of a car and executes the sequence of actions required to physically build it into existence. And because you have that factory process, you can generate multiple unique objects from a single blueprint. The constructor can rapidly produce distinct variations, like a red car, a blue car, or a green car, each occupying its own memory and holding its own specific values, all derived from one original design. This blueprint-to-object pipeline establishes the first crucial layer of order and scalability in software design. Even with blueprints, developers face the problem of redundancy. If you need to build a program that features cars, motorcycles, and buses, writing an entirely new set of instructions for the engines, wheels, and brakes of each vehicle is a massive waste of time. The solution is inheritance. Instead of starting from scratch, a specialized subclass automatically acquires all the common properties of a broader, general parent class. A sedan and a sports car simply inherit the universal traits of an automobile, meaning the developer only defines shared features once. But inheritance creates a new issue: rigidity. Sometimes, objects that share a parent class need to perform the exact same action, but in entirely different ways. To give code the freedom to adapt, developers use polymorphism, the ability of one object to adopt multiple behaviors depending on its environment. Just like a single person acts as a student in a classroom, a son at home, or a customer in a shopping mall, a piece of code can shift its function based on the context. Technically, this is executed through method overriding. If a sports car and a school bus both inherit a drive command from their parent class, the child class can rewrite that specific behavior to suit its exact needs. Inheritance saves time by establishing a family tree, while polymorphism allows individual objects to adapt to their context, providing a structure that remains manageable even as the software grows in complexity. Once you have millions of objects running in a program, a new threat emerges: interference. If every part of an application is allowed to touch and modify every other part, data gets corrupted and the system breaks. To prevent this, code uses encapsulation. This means locking vulnerable variables away privately and exposing only safe public methods to interact with them. You don't let the user touch the spark plugs directly. You encase the volatile parts and give them a gas pedal. But even with safe methods, exposing end users or other developers to the raw mechanics of how a program works causes analysis paralysis. We strip away that noise using abstraction. Abstraction is the creation of a simplified interface where all complex internal execution is intentionally hidden. When you use an ATM, you are presented with simple options: withdraw or deposit, while the complex banking logic happens out of sight. These two concepts work in tandem. Encapsulation protects the code's integrity from the user's unpredictable actions, whereas abstraction protects the user from the code's overwhelming complexity. We have moved from a chaotic, tangled list of fragile commands to a modular, secure, and highly ordered software architecture. Because code is now encapsulated, inherited, and cleanly abstracted, thousands of developers across the globe can work on the exact same application at the exact same time without their code causing a catastrophic collision. Every interface element on your screen, the play button, the volume slider, and the progress bar, is a discrete object generated from a hidden class and functioning within a rigorous hierarchy. Ultimately, object-oriented programming brings the predictable laws of physical reality to the digital world. It remains the primary philosophy for managing the massive levels of complexity found in the platforms we use every day.